Thanks for the opportunity to present here. So I'm coming from ELI Beamlines, and I also should give credit to the Institute of Plasma Physics and my alma mater, the Czech Technical University. So I would like to say something about the laser plasma modeling with high order finite elements. So this is the outline of the presentation, and we are going to start with an introduction to the topic, and then we will dive to the specific models we use, like the two-temperature hydro, laser absorption, MHD, heat diffusion, non-local energy transport, and Vlasov, Fokker, Planck, Maxwell. So laser plasma modeling, what is it about? So we need some lasers, like the 10 petawatt system L4 at ELI Beamlines, for example. And this laser then interacts with matter inside an interaction chamber, like P3, also at ELI. And the laser gets absorbed, refracted, scattered, and so on. And through this process, it creates plasma. But this is not that straightforward process at all. We have that intermediate regime of warm dense matter, energy transport inside the target and outside, generated magnetic fields, and accelerated species forward and backward, and so on and so on. Then getting to the modeling, I specialize on continuum modeling, and that's where MFEM and GLVs come in. And I may enjoy support of many different types of finite elements, and also scalability and flexibility of the libraries. So what are the applications of these? There are, of course, many, but just mentioning those I work on, it could be prepulses of ultra-intense lasers. So the prepulses cause generation of preplasma, which then filaments the main pulse in intensities, and you may see also the electron densities here. But due to a clever design of the target, we may tame this mechanism and actually even increase the intensity and contrast of the laser. A similar concept can be used then for laser ion acceleration to optimize the parameters of that ion beam here, for example. Another topic, then laboratory astrophysics and also inertial confinement fusion, where we might be interested in simulations of preheats in front of propagating shock waves. So what models do we use? The basis is the two-temperature hydrodynamics, where we approximate the plasma as an inviscid, compressible, and quasi-neutral fluid, where we prefer the Lagrangian formulation, meaning that the computational mesh follows the flow of the material, as you may see here. And probably you are familiar with that governing Euler's equations for mass, momentum, and electron and ion energies. We do a little trick here. So the primary variable for us is the temperature instead of the internal energy. So we don't have to invert this equation of state, which might be quite expensive for realistic ones. And on the numerical side, we employ the high-order curvilinear finite element hydrodynamics that was proposed by Tsanios group. There are L2 positive elements for the thermodynamic quantities and H1 elements for the kinematic. What's nice, it's compatible with classical staggered hydro, and it conserves mass pretty much everywhere. due to strong mass conservation. Together then with the conserving energy conserving time integration, we conserve momentum and energy, and that little trick with that temperatures is accounted for by this SSI-like correction. The temperature relaxation is then treated separately to not limit the time step. And then we need a laser. So the simplest thing one might think about is just attenuation of the laser in a single direction, which is known as VKB approximation. And for that, we use upwinded TG finite elements. Somewhat more sophisticated model is then ray tracing, developed by my student, which also solves this ray equation for the direction of the rays. And it's not only about that, but there is additional physics that can be included then, like resonant absorption, Fresnel equations, and actually X-ray laser amplification. But in order to accommodate it for that high order hydro, we need to do transition from high order elements to low order refined elements like here, and then back again from that low order to high order, conserving that absorbed power. But from the physical point of view, this is still not a complete answer, because the only self-consistent model in the vicinity of the critical plane is a wave-based one. So we rely here on the stationary Maxwell's equations, which give us a 1D self-consistent model, which we solve semi-analytically, so we don't have to resolve the wavelengths of the laser. But if we can, we may then apply the finite element method. And the newest addition is the resistive MHD. So we split it to the ideal part and resistive part. So the new terms here are the magnetic stress tensor, Faraday's law, Ohm's law, Joule heating, and an auxiliary equation for the specific magnetic energy. We then use HDIF or integral L2 finite elements for the magnetic field. And this way, the magnetic field remains divergence free and the magnetic flux is conserved. And also the total energy is conserved. The construction is analogous to the classical hydro. There is just a little corrective term. And moving to the magnetodynamic part, we use H-curl or H1 finite elements for the electric field. And then due to the RAM system and the discrete curl operator, we have still a divergence-free magnetic field here, but we may have explicit, semi-implicit, or fully implicit system for the electric field. So it accounts for even strongly diffusive conditions. And due to reformulation of the Joule heating, we get a nice symmetry between the energy equations, and you may convince yourself that actually this conserves the total energy perfectly. And then moving to heat diffusion, it sounds very simple, but actually it's not. It's not, because the heat conductivity in plasma is strongly temperature dependent. So we need to do nonlinear transformation, but the heat fluxes are invariant of this transformation. So we solve the problem for the heat fluxes and then update in a conservative way the temperatures based on the original equation. Another thing is that we must apply some flux limiters, because it's known that classical diffusive theory overestimates the heat fluxes. And the only self-consistent answer can be given by non-local transport methods. And that's why we are also interested in those. And I will talk about them in a while. So then numerically, we formulate the dual flux formulation, which is inherently energy conserving, and eventually we apply hybridization on it. So we have that flux is an HDiff, and then we may update the temperatures back again. And moving to that promised non-local transport model, the simplest one we have is based on the BGK operator in the kinetic equation. So it's actually the first principal model. And kinetic equation for electrons is then integrated over all velocity magnitudes, but preserving all angles. So it's still a multi-D problem. And what we obtain is a structure very much familiar to everyone doing radiation transport. So we may solve for electrons and photons in a single loop here. On the numerical side, we apply also a linearization of the sources, or the source functions, depending on the temperature, meaning that we may get an implicit system for the temperatures and or intensities, and we then apply hybridized DGs in space and DGs or H1 elements in angles. And this yields something like discrete ordinates method, but with high orders. But if we want really transient and spectrally resolved non-local transport, even with non-local fields, we need to use something even a bit more advanced, and that's that Vlasov, Fokker, Planck, Maxwell. We may then solve even such problem as heat flux over such a steep slope of temperature, where you may see that the distribution function is strongly deviated. But to simplify the things, we expand that distribution function to that isotropic part, and first single directional anisotropic correction. And this gives us the system of these two equations plus Maxwell's equations for the fields. Still, this converges in the diffusion limit to the full Braginski resistive MHD, so we haven't lost that much. And we have that non-local transport on top of it. On the numerical side, again, finite elements of arbitrary order, where we use L2 elements for F0, H1 for F1, and somewhat unusually, HDiff finite elements for E and H curl for the magnetic field. The reason is to maintain consistency between charge and mass, and together with the staggered finite differences for velocities, we have mass, charge, and energy conserving implicit numerical scheme. So we are not limited not limited in the time step that much. Concluding, we have introduced the topic of laser plasma modeling and described most of the methods we have in our multi-D multi-physics code P2, including that non-local transport. But when we want to be really accurate in that modeling, we need to shift to that Vlasov, Fokker, Planck, Maxwell instead. And what's next? Basically hybrid modeling, non-local transport, extended MHD, and maybe something else. So basically more physics and more finite elements. And also a little self-promo. I'm looking for a postdoc position for myself. So if anyone is interested into what I was doing, don't hesitate to contact me. Thank you for your attention.